Alright, see, ladies and gentlemen, oh shoot, the camera, I just hit it. Anyway, so everyone knew problem 1.6. 1.6 says, determine which of any of the following functions have properties of autocorrelation function. Justify your determination. Note FR of tau must be a non-negative function. Why? Alright, well, so they want us to find autocorrelation. Autocorrelation is when you see how well a function is correlated to itself. So what I mean by that is take the integral from minus infinity to infinity, I believe, of x of t plus x of tau plus t, for example. This is going to be x of tau with respect to d tau. And so what you're saying, you have a function with some value on the x plane. It's a relative to tau. Tau is time. And then we shift it by t seconds or t minutes, whatever it is, and then we integrate underneath that curve, and the integration underneath that curve tells us how well correlated this function is with a time shifted version of itself. And so this can be useful because, for example, in radar, you have a signal, you send it out, right? It bounces off some object, and then you get the reflection. The reflection can be seen as this part right here, right? This is the reflection that you get back. And this is the original signal. And so that reflection, obviously, because it's passing through objects, or it may have passed through objects, or it went some distance into space and came back, you know, it's the signal's attenuated, and it may have some shift, frequency, or phase shift. And so then when you multiply them back together and take the area, you get to see like, oh, is it perfectly the exact same signal with just some time shift, or was it attenuated? And basically the difference between these two can tell you, you know, can help you to infer, you know, how far the signal went or what object hit, things like that. So that's how this can be applied. Like in a simple example in terms of radar, there are many other applications for autocorrelation, but this is just one example, and it's very important in a lot of systems. And so it's important for us to show and be able to prove that a function can be autocorrelated and has the properties of autocorrelation. So the properties of autocorrelation function, usually it's different for a power signal and an energy signal, but about the same. They just have like one or two differences. For any signal, Rx of tau has to be equal to Rx of minus tau. So the function, this basically says the function, the autocorrelation function has to be even. Rx of tau. So Rx of tau has to have a maximum. So it has to be less than or equal to, and this is the absolute value of Rx of tau, to be less than or equal to Rx of 0. So that's 0 is basically when the functions are perfectly aligned with one another, which should give us the maximum area, right? So when two functions are perfectly aligned, for example, let's say we have a box function, and we have a box, another box here, right? And this is when t is equal to 0. So this is tau is equal. Let's just say tau is equal to -1, and tau is equal to 1 here, and then here. And this is when t is equal to 0. So when t is equal to 0, they're perfectly in line with one another. So you get the area underneath, it's just going to end up turning into x squared of tau. And so you should get a maximum area underneath this. So anytime you shift it, you know, the areas are not going to be fully aligned. For example, when you shift it here, let's say it's here, right? Then all you integrate is this area right here. And this area is clearly less than this area. And so you get to see that the area underneath the curve, when they're perfectly aligned, should give us the maximum. And that's at Rx is equal to 0, so that's when the time shift is 0. And they're perfectly aligned, you multiply, and you basically just get x squared of tau. So that has to be true. So max when perfect alignment. And then the Fourier transform of Rx of tau has to form a transform pair. That's either going to be for a periodic signal, or I'm sorry, for an energy signal, it's going to be psi x of f, or it's going to be gx of f for a power signal, right? And it has to be a non-negative. It has to be non-negative. right? Because these two functions are absolute values and squares, and so when you have squares and absolute values, they're always going to be non-negative. So if it's negative, you know this is not true. And then the last property, it has to be, well, the last property is really not too important. Hold on, give me a minute. I just wanna get ready. Okay, so the last property, which is important to note, and I always forget about it, but basically it says Rx of 0 for a power signal. So for a power signal, Rx of 0 will be equal to 1 over T naught times minus T naught over 2, positive T over 2, x squared T. Which is what I set up here, right? X squared to tau. And then for an energy signal, it's going to be, so this is for power. Obviously, for an energy signal, it's going to be minus infinity, positive infinity of x squared to T dt. But this condition right here, what I'll make mention about this condition is that for this condition here, it's an extension of it's an extension of condition 3. And condition 3 is this condition right here. So this condition is an extension of this. So once, if you prove all 3 of these, then 4, really, you don't have to prove this one. So I usually don't go through proving this one. I just prove that one of these is not true. So it's really an extension of all 3 of those conditions being true. All 3 of those conditions are true, and then there's no point to prove that 4 is true. You only need these 3 to be true to show that a function is, in fact, an autocorrelation function. And so let's now that we know what autocorrelation is, ooh, I just put a mark on my wall. That's not cute. I'll have to wipe that off. Let's go ahead and let's go ahead and see if these functions are autocorrelation or not. So I'm just going to erase there quickly, and then we'll start this video. All right, so we're back. So let's prove to see if these functions are going to be autocorrelation functions. Let's start with number 1. Number 1 says a x of tau is equal to 1, 0, 4. So it's a piecewise. So our first one's a piecewise for minus 1 less than or equal to tau less than or equal to 1 and 0 otherwise. So that means we have rect. Rect from minus 1 to 1 with an amplitude of 1. This is tau, this is x tau. Alright, so first we have to show that we're going to show that Rx of tau is indeed equal to so Rx of tau, they gave us x of tau. So now we need to compute Rx of tau. So for this one, Rx of tau will be equal to minus infinity to infinity of x of tau plus x of tau plus t d tau. Well, that's going to be a rect, so this is going to end up being a rect of tau times rect of tau plus t dt d tau. And so when you convolve these two together, or when you multiply this is the same thing as doing convolution. A rect convolved with a rect, it's going to be a triangle, so you end up with a triangle. So Rx of tau will end up being a triangle and should have the same bounds, I think. I think it has 1/2 of the let me do this correctly. I think this is 1/2 here. I'll check this later though. We don't need to prove this is 1/2, but we can just show this 1/2. You can go through and compute why that's the case, but really how you do this is a convolution, so this is really a rect of tau, convolve with rect of tau. Anytime you're doing autocorrelation, it technically is convolution. And so what you do is you have a box, right? And then you have a second box that's basically getting slid through this box in time. So, and it slides through it in different sections. This is the first section where only a little bit of the first box is slid into the second box. And then you have a point where it slid into a little bit at the point where they're both equals here. That's going to be an Rx of 0. So this is when t. So t is the sliding factor. So this is when t is less than 0. Because so it's t greater than 0. This is when t is less than 0. This is when t is 0, and then we have when t is equal or less than 0. So when t is less than 0, then the box has started to slide on the right side of the box. So here we go. We got this box, then we have this box here. And so each point in these, we're going to take the area underneath. So this is the area here. So for a rect, this part is 0 here. This part is 0, and this part is 1. So you're not gonna multiply this part. You're gonna multiply that part. For this part, you're just gonna take the area underneath, and then for this part, it's this area, and everything else is canceled out. This doesn't get integrated. That doesn't get integrated. And so here you have some t shift, and then you have a tau, or you have 1 here rather, and then you have a height of 1, and over here you have 1 times. This is 2 and then times 1, so be 2 times 1. That should be 2. This is minus 1 to 1, so that's the area underneath. Here it's going to be this area, which is minus 1 t times 1. So over here we get minus 1 plus t for this one, and over here we get 1 plus t. So it turns into a piecewise. The piecewise is the trie, really. So the trie definition for this specific one, so trie of tau is going to be equal to, for t greater than 0, it's going to be minus 1 plus t. For t is equal to 0, we're going to get 2, and then for t less than 0, we get 1 plus t. And that, if you plug in values for t, for example, like plug in t is equal to 1, you get 0 here. Plug in t is equal to minus 1, you're going to get 0 here, which matches up with the triangle. So that's where I get this trie from. So Rx of t is equal to trie tau. So now we have to see if this trie of tau satisfies the properties of autocorrelation. Well, trie of tau is even, so because the left hand side matches the right hand side, so trie of tau is equal to trie of minus tau. That checks off. Trie of tau, so the absolute value of it is less than or equal to trie of 0. This is basically saying the maximum at the origin, which is true. The maximum here is 2. And what else? Then we have trie of tau has the form of Fourier transform pair with the energy spectral density of the original function, but it also has to be non-negative. So we just take the integral now, which is 6 squared of f. That matches up because this is rect of f. So if we find the power spectral density, this is a power signal. This is an energy signal. I'm sorry. Take the energy spectral density. it's going to be sinc and then sinc squared of f. So this matches up. So this checks off as a, this is yes. This is an autocorrelation function. Correlation function. So that works. This checks out. Everything checks out there. Now we need to check B. We need to check part B. That was just part A. So now let's check part B. Let me erase this. The erasing part always takes a long time. I gotta get a better eraser. We have some paper towels in here actually. Let me go look see.